There are regions of the universe that have never communicated with each other. They are separated by such vast distances that not even light, traveling at 300,000 kilometers per second for 13.8 billion years, could have connected them. These regions have been causally isolated since the moment of the Big Bang itself. And yet, they are identical. Same temperature, same density, same structure, down to 1 part in 100,000. This shouldn't be possible. It violates everything we understand about cause and effect, about information transfer, about the fundamental structure of reality itself. Imagine two strangers on opposite sides of Earth who have never met, never communicated, who speak different languages, and come from completely different cultures, yet they're wearing the exact same outfit, have the same thoughts, and are performing the same actions at the same moment. That's our universe. In 1981, a physicist named Alan Guth proposed an answer so radical, so mathematically violent, that it suggested the universe we see today is just an infinitesimally small bubble in an eternally inflating multiverse. An answer that implies our cosmos expanded faster than light itself. In fact, expanded by a factor of 10 to the power of 26 in less time than it takes light to cross an atom. Today, we journey through evidence that challenges everything we thought we knew about the beginning of time, the nature of space itself, and whether our universe is truly unique.
Prepare yourselves, we begin.
In 1964, two radio astronomers at Bell Labs named Arno Penzias and Robert Wilson were trying to eliminate an annoying hiss from their antenna. No matter what they did, no matter where they pointed their instrument, no matter what time of day or night, the hiss persisted. They even cleaned out pigeon droppings, thinking birds might be the culprit. They weren't. What Penzias and Wilson had discovered was the afterglow of creation itself, the cosmic microwave background radiation. This is the oldest light in the universe, released 380,000 years after the Big Bang, when the cosmos finally cooled enough for atoms to form and photons to travel freely. This ancient light has been traveling through space for 13.8 billion years, cooling and stretching as the universe expanded, until today it appears as microwave radiation at a temperature of 2.725 Kelvin, just 2.725 degrees above absolute zero. But here's what troubled cosmologists. When they measured this radiation from opposite sides of the sky, they found something impossible. The temperature was the same, everywhere. To understand why this is extraordinary, we need to talk about cosmic horizons. Light travels at a finite speed. Since the Big Bang happened 13.8 billion years ago, light has only had 13.8 billion years to travel. This creates a cosmic horizon, a boundary beyond which light hasn't had time to reach us. And crucially, regions beyond each other's horizons could never have exchanged information, could never have influenced each other. When we observe the cosmic microwave background, we're looking at regions of space that are now 46 billion light-years away in opposite directions, a total separation of 92 billion light-years. But here's the critical point. When that radiation was released 380,000 years after the Big Bang, those regions were causally disconnected. They were beyond each other's horizons. They had never communicated. According to relativity, nothing, no force, no particle, no information of any kind can travel faster than light. So these regions should have had completely independent temperature histories. Some should have been hotter, some colder. Random fluctuations should have created dramatic differences. Instead, they matched to within 0.001%. It's as if you scattered coins across an area the size of a continent, and when you checked them, every single one, without exception, had landed exactly on its edge. Not heads, not tails, edge. But the horizon problem was just the beginning. Physicists discovered a second mystery, equally troubling, the flatness problem. The geometry of space itself can be curved, like the surface of a sphere, or flat, like an infinite sheet of paper, or saddle-shaped, curving in opposite directions. Which geometry our universe has depends on its density, the total amount of matter and energy it contains. Here's what makes this strange. The universe is almost perfectly flat. Measurements from the Planck satellite show that if the universe has any curvature at all, it must be less than 0.4%. It's flat to within extraordinary precision. This might not sound unusual until you realize that flatness is unstable. The Big Bang should have produced a universe with some arbitrary curvature, and that curvature should have been amplified exponentially as the universe expanded. A universe that started even slightly curved should have become dramatically curved within fractions of a second. For our universe to be as flat as we observe today, the initial density 13.8 billion years ago would have had to be fine-tuned to 1 part in 10 to the power of 60. That's a decimal point followed by 59 zeros and then a 1. The initial conditions would have needed to be more precisely calibrated than anything we've ever encountered in physics. This isn't just unlikely, it demands explanation. In December 1979, a young physicist named Alan Guth was attending a lecture about magnetic monopoles, hypothetical particles predicted by grand unified theories but never observed. He was troubled by a problem. These theories predicted the universe should be swarming with monopoles, but we'd never detected a single one. That night, unable to sleep, Guth was working through equations in his notebook. He was exploring an unusual idea. What if the early universe underwent a brief period of exponential expansion driven by a peculiar form of energy embedded in space itself? At 1 a.m., he wrote in his notebook, "Spectacular realization." What Guth realized was that exponential expansion, which he called inflation, could solve multiple problems simultaneously. It would dilute magnetic monopoles to undetectable levels. It would stretch any initial curvature flat, like inflating a balloon until its surface appears perfectly smooth. And most remarkably, it would solve the horizon problem by taking a tiny region of space that was causally connected, small enough for temperature to equalize, and stretching it to cosmic scales. The idea was this: for a brief moment, approximately 10 to the power of -36 seconds after the Big Bang, the universe underwent explosive expansion. In less time than it takes light to cross a proton, space itself expanded by at least a factor of 10 to the power of 26, perhaps much more. Everything we can see, all 93 billion light-years of the observable universe, was once smaller than an atom, small enough to have reached thermal equilibrium, small enough to have been smoothed by quantum fluctuations. Then inflation stretched it, faster than light, to cosmological scales. But the evidence forces us to confront an uncomfortable possibility. If this happened once, it might still be happening, somewhere, everywhere. If inflation theory is correct, it makes specific, testable predictions. The most important involves tiny fluctuations in the cosmic microwave background temperature. Quantum mechanics tells us that empty space isn't truly empty. It seethes with virtual particles that pop in and out of existence. During inflation, these quantum fluctuations were stretched to cosmic scales, imprinted into the structure of space itself. These fluctuations should appear as tiny temperature variations in the CMB, hot spots and cold spots corresponding to regions that were slightly denser or less dense. In 1992, NASA's COBE satellite detected these fluctuations for the first time. The temperature variations were incredibly small, just 18 millionths of a Kelvin, but they were there, and they followed a specific pattern. The 2003 WMAP satellite measured these fluctuations in exquisite detail. What it found was extraordinary. The pattern of hot and cold spots matched inflation's predictions almost perfectly. The statistical distribution, the size scales, the amplitude, everything fit. In 2013, the European Space Agency's Planck satellite took measurements so precise that cosmologists could test inflation to unprecedented accuracy. The results were stunning. The fluctuations showed a nearly scale-invariant spectrum, meaning quantum fluctuations at all sizes were stretched equally during inflation, exactly as the theory predicted. The probability of this pattern arising by chance is essentially zero. These temperature fluctuations are the fossilized imprints of quantum events that occurred when the universe was 10 to the power of -36 seconds old, stretched across the entire cosmos. But the evidence goes deeper. Before the universe became transparent 380,000 years after the Big Bang, it was filled with hot plasma, a soup of electrons, protons, and photons. Sound waves rippled through this plasma, created by the initial density fluctuations from inflation. These primordial sound waves are called baryon acoustic oscillations. When atoms formed and the plasma cleared, these sound waves froze in place. They're visible today as a specific pattern in the CMB temperature fluctuations, a series of peaks and troughs when you analyze the fluctuations at different angular scales. These are called acoustic peaks. The first acoustic peak was detected by WMAP and precisely measured by Planck. It appears at an angular scale of about 1 degree on the sky. This isn't random. The peak's location depends on how far sound could travel in the plasma before atoms formed, which depends on the speed of sound in the early universe and how long the plasma existed. Planck measured 6 acoustic peaks. Their heights, positions, and spacing match inflation's predictions with staggering precision. The first peak tells us the universe is geometrically flat to within 0.4%. The second and third peaks reveal the ratio of ordinary matter to dark matter. The pattern encodes the entire history of the universe's first 380,000 years. This represents just one piece of a much larger puzzle hidden in the structure of space itself. The story doesn't end with the CMB. Those tiny temperature fluctuations, amplified by inflation from quantum noise, were also density fluctuations. Regions that were slightly denser had slightly more gravitational pull. Over hundreds of millions of years, gravity amplified these fluctuations. Dense regions attracted more matter. They grew into vast clouds of gas. Stars formed, galaxies coalesced, clusters of galaxies assembled. The cosmic web, the largest structure in the universe, emerged. Beginning in the 1980s, astronomers began mapping the three-dimensional distribution of galaxies across billions of light years. What they found was breathtaking. Galaxies aren't distributed randomly. They form an intricate web, vast filaments and sheets of galaxies surrounding enormous voids. The largest structures span 300 million light-years or more. In 2005, the Sloan Digital Sky Survey created the most detailed three-dimensional map of the universe ever made. When cosmologists analyzed this map, they found something remarkable. The statistical pattern of galaxy clustering matched the pattern of temperature fluctuations in the CMB. Think about what this means. Quantum fluctuations that occurred in the first trillionth of a trillionth of a trillionth of a trillionth of a second, stretched by inflation to cosmic scales, imprinted a pattern that we can see both in the ancient light of the CMB and in the distribution of galaxies today. The same pattern, separated by 13.4 billion years of cosmic evolution, connected by gravitational amplification of those original seeds. The odds of this correlation occurring without a common cause, without inflation, are vanishingly small. It's as if you found the same fingerprint at both a crime scene and on a suspect's hand. It's not proof beyond all doubt, but it's extraordinarily compelling evidence. But here's where it gets strange. Inflation doesn't just stretch density fluctuations, it also stretches gravitational waves, ripples in the fabric of space-time itself. During inflation, quantum fluctuations created tiny gravitational waves. These waves were then amplified by the exponential expansion, stretched to cosmic scales. Unlike the density fluctuations, which create temperature variations, these primordial gravitational waves create a specific pattern in the polarization of the CMB. Light waves oscillate in particular directions, and gravitational waves twist this polarization into distinctive swirls called B-modes. Detecting these B-modes became the holy grail of cosmology. If found, they would provide direct evidence that space-time itself underwent quantum fluctuations during inflation, proof that gravity behaves quantum mechanically, something we've never directly observed. In 2014, a team using the BICEP-2 telescope at the South Pole announced they'd detected these primordial B-modes. The news electrified the physics community. Nobel Prizes seemed imminent. But subsequent analysis revealed the signal was contaminated by dust in our own galaxy. The B-modes haven't been detected yet, But the search continues with increasingly sensitive instruments, BICEP-3, the Simons Observatory, and eventually the space-based LiteBIRD mission planned for the late 2020s. If primordial gravitational waves exist at levels inflation predicts, we will find them. The most remarkable discovery involves what inflation implies about reality itself. In the standard inflation model, a field called the inflaton field derives the exponential expansion. This field has energy, and when inflation ends, that energy converts into the hot, dense state we call the Big Bang, creating all the matter and radiation in our universe. But here's the problem. Quantum mechanics says that fields fluctuate randomly. In most regions of space, the inflaton field decays and inflation ends, creating a bubble universe like ours. But in some regions, quantum fluctuations push the field upward and inflation continues. This creates more space, which means more regions where inflation can either end or continue, which creates even more space.
The process never stops. This is called eternal inflation, and it's not a speculative addition to the theory. It emerges naturally from the same quantum mechanics that successfully predicts the CMB fluctuations. Andre Linde, one of inflation's pioneers, realized this in the early 1980s. Inflation isn't just something that happened once in our cosmic past, it's something that's happening eternally, creating an infinite multiverse of bubble universes.
Each bubble universe can have different physical properties. The strength of fundamental forces might vary, the masses of particles might differ, the number of spatial dimensions could change. Most bubbles would be sterile, unable to support complex structures, let alone life. But in an infinite multiverse, every possibility that can occur will occur, infinitely many times. Our universe, with its precise balance of forces that allows atoms, stars, planets, and life, is just one bubble in an eternally inflating foam of universes. The question isn't why our universe has the properties it does. The question is, could it be any other way?
This leads to a profound crisis in physics called the measure problem. In an eternally inflating multiverse, there are infinitely many bubble universes, infinitely many with physical laws like ours, infinitely many with slightly different laws, infinitely many with wildly different laws. When you're dealing with infinite sets, how do you calculate probabilities? How do you make predictions? Imagine trying to answer the question, are there more even numbers or more odd numbers? Both sets are infinite, so the question has no meaningful answer without additional rules. The same problem plagues eternal inflation. Physicists have proposed various measures, mathematical prescriptions for comparing infinite quantities, but different measures give different predictions. Some suggest our universe is typical, others suggest it's extraordinarily unusual. The lack of a universally accepted measure remains one of the deepest unsolved problems in theoretical physics.
And it gets stranger. Some versions of eternal inflation suggest that every quantum event creates a branching universe. Every time a particle's wave function collapses, reality splits. This means there are copies of you, perhaps infinitely many, making different choices, living different lives in other bubble universes. The evidence extends beyond cosmology, into the realm of fundamental physics, quantum mechanics, and the nature of reality itself. We're forced to confront questions that once belonged to philosophy, not science. Questions about identity, uniqueness, and what it means to exist.
To understand inflation theory fully, we need to examine its mechanism, the inflaton field. Fields are fundamental to modern physics. The electromagnetic field carries light. The Higgs field gives particles mass. The inflaton field, whatever it is, drove cosmic inflation. We don't know exactly what the inflaton field is. It's not been directly detected, and it might be related to fields we already know or something entirely new. What we do know is its behavior. The inflaton field has a potential energy, like a ball sitting on a hill. When the field sits at high values on this potential, space itself has enormous vacuum energy. This energy creates a repulsive gravitational effect, negative pressure, that drives exponential expansion.
As inflation proceeds, the field slowly rolls down its potential, like a ball rolling down a gradual slope. When it reaches the bottom, inflation ends abruptly. The field's potential energy converts into kinetic energy, which decays into particles, quarks, electrons, photons, creating the hot, dense state we call the Big Bang. This process is called reheating, and it's essential. Without reheating, inflation would create a cold, empty universe. With reheating, it creates our universe, filled with matter, energy, and eventually, us. Paul Steinhardt and Andreas Albrecht developed much of this framework in 1982, independently confirming Guth's insight and making it mathematically rigorous. Andre Linde extended the theory, showing how different regions could inflate at different times, creating a multiverse landscape.
Inflation isn't the only game in town. Some physicists argue that the horizon and flatness problems might be solved by alternatives. Paul Steinhardt and Neil Turok proposed the cyclic model, where the universe undergoes infinite cycles of expansion and contraction. Each cycle resets the universe, solving fine-tuning problems through repetition rather than inflation. Roger Penrose proposed conformal cyclic cosmology, where the infinite future of one universe becomes the Big Bang of the next. His theory makes specific predictions about patterns in the CMB that might already be present in the data. Circular features called Hawking points, where black holes from the previous universe evaporated. String theory offers its own version of inflation, called brane inflation, where our universe is a membrane floating in higher dimensional space. Inflation occurs when branes collide, converting kinetic energy into matter and radiation. Yet despite these alternatives, inflation remains the dominant framework. Why? Because it makes testable predictions that have been confirmed, the CMB fluctuations, the acoustic peaks, the large-scale structure. These observations don't prove inflation beyond all doubt, but they strongly constrain any alternative theory.
What do leading physicists believe? Alan Guth, now a professor at MIT, remains convinced that inflation explains the observable universe's properties better than any alternative. But he acknowledges the eternal inflation problem. Once inflation starts, it never completely stops, leading to an infinite multiverse. Andre Linde at Stanford emphasizes the theory's predictive power. Inflation predicted the cosmic microwave background fluctuations should be scale invariant and Gaussian. Both predictions were confirmed with extraordinary precision. Paul Steinhardt, ironically, has become one of inflation's most vocal critics. He argues that eternal inflation makes the theory unprovable because it predicts everything and therefore predicts nothing. His concern is that without a solution to the measure problem, inflation loses its scientific character. Max Tegmark at MIT takes a different view. He embraces the multiverse implications, arguing that if infinite universes exist, every possible physical configuration must occur somewhere. This forces us to reconsider fundamental assumptions about scientific explanation and what it means for a theory to be successful. The debate continues, but one thing is clear: inflation has transformed cosmology from a field of speculation into a precision science with testable predictions and observational confirmation. Recent breakthroughs suggest we're entering a golden age of precision cosmology. The James Webb Space Telescope, launched in 2021, is revolutionizing our understanding of the early universe. By observing galaxies that formed just 200 million years after the Big Bang, JWST is testing whether inflation correctly predicts the initial density fluctuations that seeded galaxy formation. Early results show galaxies appearing earlier and more massive than expected, a puzzle that may require modifications to our understanding of inflation or structure formation. Ground-based instruments are pushing the boundaries of CMB observation. The Simons Observatory in Chile's Atacama Desert, coming online in 2024, will map polarization patterns with unprecedented sensitivity. The CMB-S4 project, a network of telescopes planned for the late 2020s, aims to detect primordial B modes if they exist at levels inflation predicts. But the most ambitious project is LiteBIRD, a Japanese-led space mission scheduled for launch in the early 2030s. Operating beyond Earth's atmosphere, LiteBIRD will measure CMB polarization across the entire sky with precision that would definitively detect or rule out primordial gravitational waves from inflation. If B modes are found, it would confirm that quantum mechanics applies to gravity itself, unifying quantum theory with general relativity at the moment of cosmic origin. If they're not found at predicted levels, inflation theory would need radical revision.
What scientists discovered next would change everything about how we think about inflation's aftermath. For the past decade, cosmologists have been troubled by a discrepancy called the Hubble tension. The Hubble constant measures how fast the universe is expanding. When you calculate it using the CMB, looking at the early universe, you get one value, about 67 kilometers per second per megaparsec. When you measure it directly using nearby supernovae, looking at the late universe, you get a different value, about 73. This might not sound dramatic, but it's a 5 sigma discrepancy. Physicists speak for almost certainly real, not a statistical fluke. It's as if you measured your height in the morning and found you were 6 feet tall, then measured again in the evening and found you were 7 feet tall. Something is wrong. Either our measurements have systematic errors we haven't identified, or our understanding of cosmic expansion is incomplete. Some physicists propose that inflation's details might differ from standard models. Others suggest exotic new physics, perhaps dark energy evolved over time, or additional particles we haven't discovered affect expansion rates. The tension could be a crack in the cosmological model, a hint that inflation, while solving many problems, doesn't capture the complete story of cosmic evolution. The most profound implications emerge when we consider inflation's quantum foundations. Standard inflation assumes the inflaton field starts with some classical value, a specific energy density and spatial distribution. But where did that initial state come from? Before inflation, before time itself, what determined the inflaton field's configuration? This leads to ideas about quantum cosmology, the application of quantum mechanics to the entire universe. Alexander Vilenkin proposed that the universe tunneled into existence from nothing, a quantum fluctuation that created space, time, and the inflaton field simultaneously. Stephen Hawking and James Hartle developed the no-boundary proposal, suggesting the universe's beginning is smooth and finite but has no edge or boundary, like the surface of a sphere. These ideas are extraordinarily speculative, pushing physics into regimes where we have no experimental guidance. Yet they emerge naturally when we take inflation seriously and ask what came before. If inflation can create our universe from a quantum fluctuation, why couldn't it create itself? Some physicists argue this shows the limits of scientific explanation. Others see it as the frontier of human understanding, the point where physics meets metaphysics, where equations encounter existence itself. What remains clear is that inflation doesn't just solve problems in cosmology. It raises profound questions about causation, existence, and whether our universe requires an explanation beyond physical law. Questions that push us toward the boundaries of what science can address. The most disturbing evidence comes from taking inflation's predictions to their logical conclusions. If eternal inflation is correct, then everything that can happen will happen, infinitely many times. There are infinite copies of you reading these words, infinite variations where you made different choices, infinite universes where history unfolded differently, where dinosaurs never went extinct, where humans never evolved, where Earth never formed. But it goes further. In an infinite multiverse, finite patterns must repeat. Your exact configuration of atoms, your precise memories and experiences must recur infinitely often.
Most of these copies exist in universes similar to ours. But some exist in radically different contexts, perhaps as isolated brains floating in empty space, complete with false memories of a past that never occurred. This is called the Boltzmann brain problem, and it's deeply troubling. If typical observers in an eternally inflating multiverse are isolated brains rather than evolved creatures in stable universes, then our own existence is extraordinarily unlikely. Every assumption we make about our surroundings could be wrong.
Physicists have proposed solutions. Perhaps the measure problem can be solved in ways that make ordered universes like ours more typical than Boltzmann brains. Perhaps eternal inflation is wrong, and inflation ended globally after some finite duration. Perhaps we're fundamentally misunderstanding probability in infinite contexts. But the fact remains, inflation's success at explaining our observations comes at a profound philosophical cost. It suggests reality is vastly larger and stranger than the universe we observe. It implies that our existence might be one instance in an infinite ensemble, no more unique than a single grain of sand on an infinite beach.
Consider another implication, the origin of time's arrow. We perceive time as flowing forward. Eggs break but don't unbreak. Memories form but don't dissolve. Entropy increases but never decreases. Yet the fundamental laws of physics are time-symmetric. The equations work equally well forward or backward in time. So why does time have a direction? The standard answer involves the second law of thermodynamics. Entropy increases because the universe started in an extremely low entropy state. But this just pushes the question back. Why did the universe begin with low entropy? Inflation provides an answer. During inflation, space expands so rapidly that any pre-existing entropy is diluted to essentially zero. Inflation creates an enormous, nearly homogeneous universe in an extremely low entropy state, precisely the initial conditions needed for the second law to operate and time to have an arrow. But here's the remarkable part. Inflation simultaneously explains why the universe is smooth enough to support structure formation and why time flows in a particular direction. Both emerge from the same mechanism. The exponential expansion that solved the horizon problem also solved the entropy problem. This suggests something profound. Time's arrow isn't fundamental. It's a consequence of cosmological evolution, an emergent property arising from inflation's dynamics. In a universe without inflation, time might have no preferred direction, or might not exist in any meaningful sense at all. Recent observations reveal patterns that push us toward a startling possibility. If inflation creates infinite universes, and if intelligent life is possible in many of them, then civilizations far more advanced than ours likely exist. Some might develop the capacity to simulate universes computationally, creating virtual cosmoses with virtual inhabitants, perhaps to study cosmology or simply because they can. In an infinite multiverse, the number of simulated universes would vastly outnumber real ones. If simulations are possible and civilizations create them, then statistically, we're more likely to be simulated entities than original ones. This is a modern version of the simulation hypothesis, turbocharged by inflation. It's not just speculative philosophy, it follows from taking inflation's predictions seriously and applying them to the question of what advanced civilizations might do. Some physicists argue we might detect evidence of simulation through glitches or computational shortcuts in the laws of physics. Others point to the universe's mathematical structure, the fact that reality seems to run on equations as suggestive. Max Tegmark has proposed that mathematical structures are reality, that the universe doesn't just act like it's following equations, but literally is a mathematical object. These ideas venture beyond conventional science into territory that makes many physicists uncomfortable, yet they emerge from following the evidence about inflation and asking uncomfortable questions about what it implies. If our universe is one bubble in an infinite multiverse, if infinite civilizations exist with technology beyond our imagination, If reality itself might be computational, then certainty about anything becomes impossible. The most profound implications emerge when we consider that inflation, quantum mechanics, and information theory might all be pointing toward a single unsettling conclusion: reality is not what it seems. The universe we observe might be a small, atypical slice of something far vaster. Our understanding might be fundamentally limited, not by our intelligence or our instruments, but by the very nature of existence within an infinitely inflating multiverse. We began with a mystery: why regions of the universe that could never have communicated are identical in temperature. We've journeyed through evidence that challenges our understanding of beginnings. We've seen how quantum fluctuations smaller than atoms were stretched to cosmic scales, imprinting patterns we can still detect 13.8 billion years later. We've explored how inflation solves multiple problems simultaneously: the horizon problem, the flatness problem, the monopole problem, with a single mechanism: exponential expansion driven by vacuum energy. We've confronted the implications: eternal inflation creating infinite bubble universes, each with potentially different physical laws; the measure problem that makes prediction impossible in infinite contexts; Boltzmann brains that threaten our understanding of what it means to be typical; the arrow of time emerging from cosmological evolution rather than fundamental law. What have we learned? That the universe is far stranger than our ancestors imagined. That the observable cosmos, all 93 billion light-years of it, might be an infinitesimally small bubble in an eternally inflating expanse. That quantum mechanics and gravity intertwine at the moment of cosmic origin. That our existence might not be unique, but one instance in an infinite ensemble. The current scientific consensus is clear: inflation remains the best explanation for the universe's large-scale properties. The CMB fluctuations, acoustic peaks, and large-scale structure all match predictions. But the theory's implications remain deeply troubling, pushing physics toward questions about existence, uniqueness, and the limits of scientific explanation.
As we peer deeper into cosmic history with ever more sophisticated instruments, JWST, LiteBIRD, next-generation gravitational wave detectors, we move closer to understanding what happened in the first trillionth of a trillionth of a trillionth of a second. We move closer to knowing whether primordial gravitational waves rippled through space-time, carrying proof that quantum mechanics and gravity unified at the moment of creation. But perhaps the most important lesson is this: the universe remembers what it shouldn't. Causally disconnected regions share identical properties. Quantum fluctuations from beyond space and time itself have shaped cosmic structure. The very fact that we can decode these patterns, extract this information, understand these origins, this itself is remarkable.
We are the universe attempting to understand itself, using instruments forged from star stuff to peer back at the moment of cosmic origin, finding in the ancient light of creation whispers of an eternal multiverse we may never fully explore. The cosmos is vast beyond measure. The mysteries are endless and profound. The journey continues through observation, through theory, through the relentless human drive to understand our place in existence. And in that journey lies perhaps the deepest truth: that consciousness arising from quantum fluctuations stretched by inflation can comprehend its own origins is as miraculous as any of the phenomena we've explored. The universe remembers, and through us, it knows. Empty space is not empty. Right now, in the void between your atoms, in the darkness between stars, in the vast nothingness between galaxies, space itself is seething with activity. Particles blink into existence and vanish in trillionths of a second. Energy fluctuates wildly at quantum scales. The vacuum writhes with invisible fields that shape reality itself. This isn't poetry, it's physics. In 1948, a Dutch physicist named Hendrik Casimir predicted that two metal plates placed close together in a perfect vacuum would experience an attractive force, not from gravity, not from electromagnetism, but from the quantum properties of empty space itself. When experimenters tested this prediction, they found he was correct. The vacuum was pushing the plates together. Empty space has pressure, it has energy, and according to our best theories of cosmology, it once had enough energy to create the entire observable universe in a fraction of a second. The implications are staggering. If quantum vacuum fluctuations powered cosmic inflation, then everything we see, every galaxy, every star, every atom in your body, emerged from literally nothing. Not from a pre-existing particle or field, but from the quantum foam of space-time itself. From borrowed energy that the universe never had to repay. Today, we explore evidence that the vacuum is not passive background, but active participant, the hidden force that birthed reality, the quantum ghost that haunts the cosmic machine.
Ongoing research is pursuing dark matter through multiple strategies simultaneously. Direct detection experiments deep underground use tanks of liquid xenon or other materials, waiting for a dark matter particle to collide with an atomic nucleus. The largest current experiment, LUX-ZEPLIN in South Dakota, uses 7 tons of liquid xenon and can detect collisions producing energies as small as a few keV. These experiments operate deep underground, 1,600 meters below the surface for LUX-ZEPLIN, to shield against cosmic rays. They cool detectors to near absolute zero to minimize thermal noise. They use the purest materials ever manufactured to eliminate radioactive contamination. And so far, after decades of progressively more sensitive searches, they've found nothing definitive. The lack of signal is ruling out vast swaths of theoretical parameter space, telling us what dark matter isn't, even if we can't yet discover what it is.
Recent breakthroughs suggest new search strategies. The ADMX experiment at the University of Washington searches for axions using a high-powered magnet and sensitive radio receivers. If axions exist and pass through a strong magnetic field, they should convert into photons at specific frequencies related to the axion mass. ADMX has been operating for over 2 decades, gradually scanning through possible axion masses. In 2018, they reached sensitivity capable of detecting even pessimistic axion models, entering territory where discovery becomes plausible. Meanwhile, the Fermi Gamma Ray Space Telescope searches for signals of dark matter annihilation in space. When dark matter particles collide, they should annihilate into gamma rays. The center of our galaxy, dwarf satellite galaxies, and galaxy clusters are prime hunting grounds. Some tantalizing hints have emerged: excess gamma rays from the galactic center, unusual signals from dwarf galaxies, but nothing definitive. The challenge is distinguishing dark matter signals from astrophysical backgrounds like pulsars and supernova remnants.
What this means for us extends beyond academic curiosity. Understanding dark matter means understanding the universe's structure and evolution. It affects the formation of galaxies, the distribution of matter, the ultimate fate of cosmic expansion. Every question about cosmic history involves dark matter. It also tests the limits of human knowledge. We're forced to study something we cannot see, touch, or directly measure. We must infer its properties from subtle gravitational effects and missing mass in cosmic accounting. This develops new ways of thinking about evidence and inference. We learn to trust mathematics and careful reasoning even when direct observation is impossible. These cognitive tools apply far beyond physics, to economics, psychology, any field dealing with invisible influences and indirect evidence. Dark matter reminds us that reality extends beyond human perception. The universe contains more than our senses reveal. Understanding it requires intellectual tools, mathematics, theory, careful reasoning that transcend direct experience. The most profound implications emerge when we consider what dark matter reveals about our place in the cosmos. We're made of atoms, protons, neutrons, electrons. These particles comprise just 15% of the universe's matter. The other 85% is fundamentally different stuff that doesn't share our physics. This means we're not just cosmically rare in terms of location or timing. We're made of rare matter. The material composing our bodies, our planet, our stars represents a minority constituent of reality. If consciousness requires the complexity enabled by chemistry, and chemistry requires electromagnetic interactions, then consciousness might be fundamentally impossible for dark matter. The vast majority of the universe's matter might be forever unconscious, unable to experience or reflect on its own existence. We occupy a strange niche, rare matter capable of understanding, observing, questioning. The universe's dominant component might be forever mute and blind, while we, the minority, achieve awareness.
What the evidence suggests about reality itself challenges our intuitions. Dark matter demonstrates that the universe is fundamentally invisible to us. The majority of substance passes through our bodies constantly without interaction. We're transparent to it. It's transparent to us. We share space but might as well inhabit different realities. This suggests a layered universe, multiple substances coexisting in the same space, each responding to gravity but otherwise operating independently. Our electromagnetic reality and dark matter's gravitational reality overlap without touching. Could there be other layers we haven't discovered? Other forms of matter responding to forces we haven't encountered? The universe might be more crowded than we imagine, filled with substances and forces beyond our current understanding. The fact that we discovered dark matter at all, through careful observation and reasoning, suggests we can eventually understand it. But it also reveals how much remains hidden. If 85% of matter went unnoticed until the 20th century, what else are we missing? Unsolved mysteries and paradoxes remain. The biggest question: what is dark matter? After 90 years since Zwicky's discovery, we still don't know. It could be WMAPs, axions, primordial black holes, sterile neutrinos, or something nobody has imagined yet. Another puzzle? Why is there exactly 5.5 times more dark matter than normal matter? This ratio seems arbitrary. No known theory explains why these two very different kinds of matter should exist in similar amounts. The missing satellites problem. Simulations predict large galaxies like the Milky Way should have thousands of small dark matter halos orbiting them. We see only a few dozen dwarf galaxies. Where are the rest? Are they dark, pure dark matter without stars? Or is something wrong with our models? Perhaps the deepest mystery? Did dark matter enable life? Without dark matter, galaxies wouldn't form properly. Stars wouldn't organize into stable structures. The universe would be a sparse, chaotic place. Life requires stable environments, planetary systems in orderly galaxies. Dark matter provides that stability. We might owe our existence to invisible scaffolding we've only recently learned to detect. Multiple possible futures emerge based on current evidence. In one future, we detect dark matter particles directly within the next decade. Experiments finally register clear signals revealing dark matter's mass, interaction strength, and properties. This opens a new chapter in physics, understanding dark matter's dynamics, searching for dark forces, perhaps discovering dark complexity. In another future, dark matter remains elusive, but we map its distribution with exquisite precision. Gravitational lensing surveys and galactic dynamics reveal exactly how dark matter clumps and flows, even if we never identify individual particles. We understand dark matter through its effects, much as we understood atoms before seeing them directly. In yet another future, experiments rule out all simple dark matter candidates, forcing radical revision of our theories. Perhaps dark matter is far more exotic than WMAPs or axions. Perhaps it involves extra dimensions, quantum gravity effects, or physics beyond our current frameworks. The most revolutionary possibility, we discovered dark matter has rich internal structure. Dark atoms, dark molecules, dark chemistry, an entire shadow world operating by different rules but sharing our space. This would transform our understanding of what the universe contains and hint at realities we've barely imagined. We've journeyed from Fritz Zwicky's 1933 observation of impossible galaxy velocities through Vera Rubin's revolution in the 1970s to today's cutting-edge searches in underground laboratories and space observatories. Along the way, we've seen evidence from rotation curves, gravitational lensing, the cosmic microwave background, and computer simulations, all pointing to the same conclusion. Dark matter is real, it dominates the universe, and we still don't know what it is. We've learned that the visible universe, everything we see, everything we're made of, represents just the tip of the cosmic iceberg. The vast majority lies hidden, detectable only through gravity's subtle pull. We've seen how dark matter shaped cosmic history, enabling galaxies to form, stars to ignite, planets to cool, and life to emerge. Without it, the universe would be a vastly different and probably empty place. Returning to our opening question with transformed understanding, yes, dark matter is passing through your body right now. Billions of particles every second, interacting so weakly you never notice. You're transparent to it. It's transparent to you. Current scientific consensus holds that dark matter consists of unknown particles produced in the early universe, distributed in vast halos surrounding galaxies and comprising 85% of all matter. But the exact nature remains uncertain. We're still searching. What remains unknown exceeds what we've learned. We don't know dark matter's mass, interaction strength, or whether it has internal structure. We don't know if there's one type or many. We don't know if it's connected to other unsolved mysteries like dark energy or cosmic inflation. But we're closer than ever. Every experiment constrains the possibilities. Every observation refines our models. Every year brings new searches with unprecedented sensitivity. Dark matter reminds us that the universe is stranger than we imagined, that most of reality operates beyond human perception. That understanding requires intellect, mathematics, and careful reasoning rather than direct experience. It shows us that we're made of rare substance, the minority of matter that can organize into complexity, chemistry, consciousness. We're cosmic outliers, using our brief moment of awareness to study the invisible foundations supporting our existence. In the vast, dark ocean of the universe, we're tiny, luminous islands asking questions about the depths below. The universe is vast. The mysteries are endless. The journey continues. Dark matter reminds us that the universe is stranger than we imagined, that most of reality operates beyond human perception, that understanding requires intellect, mathematics, and careful reasoning rather than direct experience. It shows us that we're made of rare substance, the minority of matter that can organize into complexity, chemistry, consciousness. We're cosmic outliers, using our brief moment of awareness to study the invisible foundations supporting our existence. In the vast dark ocean of the universe, we're tiny luminous islands asking questions about the depths below. The universe is vast. The mysteries are endless. The journey continues. But here's where it gets truly strange. The transition doesn't just change the physical constants, it fundamentally restructures space-time itself. The bubble interior exists in a different vacuum state, which means it has different vacuum energy, what we call the cosmological constant. General relativity tells us that vacuum energy curves space-time. Different vacuum energy means different curvature. The bubble's interior could have radically different gravitational properties than our current universe. Inside the bubble, the universe might recollapse immediately into a big crunch, or it might expand exponentially, tearing itself apart. Or it might settle into a new configuration where atoms can't form, where nuclear fusion is impossible, where life of any kind is unthinkable.
The calculations show that most possible true vacuum states would be hostile to any form of complexity. No chemistry, no stars, no galaxies, just elementary particles in a featureless void governed by alien physics. This discovery raised a question that still haunts cosmology. Is our universe stable? Physicists soon realized that answering this question requires knowing the exact values of fundamental constants, particularly the Higgs field. The Higgs field gives particles their masses. If the Higgs exists in a false vacuum state, then everything depending on particle masses exists in a false vacuum state, which means everything. But the evidence forces us to confront an uncomfortable possibility. Measurements of the Higgs boson suggest we might be living on the edge of stability, in a universe that could, at any moment, undergo the ultimate phase transition. The first real evidence came on July 4, 2012. CERN's Large Hadron Collider announced the discovery of the Higgs boson, the quantum excitation of the Higgs field that permeates all space. Teams at the ATLAS and CMS detectors had been smashing protons together at energies of 8 trillion electron volts, and they found it, a new particle with a mass of approximately 125 billion electron volts. This mass measurement was precise, 125.1 GeV, with an uncertainty of just 0.2 GeV. That precision mattered, because when physicists plugged this value into their calculations of vacuum stability, they found something disturbing. Scientists discovered that the measured Higgs mass places our universe in what they call the metastable region. Here's what that means. The stability of the vacuum depends on the relationship between the Higgs mass and the top quark mass, the heaviest fundamental particle. These two values determine whether the Higgs field sits in an absolute minimum, stable, a local minimum, metastable, or no minimum at all, unstable. The measured values put us right on the boundary. With a Higgs mass of 125 GeV and top quark mass of 173 GeV, the Higgs field exists in a shallow valley with a much deeper valley somewhere below. In 2013, researchers at CERN published calculations showing that the instability scale, the energy where tunneling becomes likely, sits around 10 to the 11 billion electron volts. That's about 100 billion times higher than the energy of the Higgs boson itself. This means the false vacuum is protected by an enormous energy barrier. Quantum tunneling through it is possible, but extremely unlikely in any given region of space at any given time. But this represents just one piece of a much larger puzzle. In 2014, physicists at the University of Southern Denmark calculated the rate of vacuum decay for our universe. They found that given the measured Higgs mass, a vacuum decay bubble could form spontaneously somewhere in our observable universe with a probability of about 1 chance in 10 to the 100 years. To put that in perspective, the universe is currently 13.8 billion years old, about 10 to 10 years. The timescale for vacuum decay is 10 to 90 times longer than the current age of the universe. This sounds safe, except for one crucial detail. We're not alone in the universe, and we're not passive observers. High-energy events, cosmic ray collisions, black hole mergers, the Big Bang itself, could potentially trigger vacuum decay. Not by providing energy to roll over the barrier, but by creating conditions where quantum tunneling becomes more likely. The most remarkable discovery involves the early universe. Cosmologists realized that during cosmic inflation, the period of exponential expansion moments after the Big Bang, the universe's energy density was enormous. Energy scales reached values that should have triggered vacuum decay instantly. Yet here we are. The universe didn't collapse into true vacuum during inflation. This puzzle has led to several interpretations. First, perhaps the inflationary field somehow stabilized the vacuum temporarily. The high energy conditions might have actually raised the energy barrier, making tunneling less likely. Second, maybe we got lucky. With only one universe to observe, we can't calculate probabilities. If vacuum decay was possible but unlikely during inflation, and we happen to exist in a region where it didn't occur, then that's the only universe we could ever observe. Third, and this is where things get really strange, perhaps vacuum decay did occur, and we're living in the bubble. Now we venture into territory where observation meets theory in unexpected ways. In 2015, researchers at Harvard discovered something troubling about the Higgs field's behavior at high energies. They calculated how the Higgs self-coupling, the way the Higgs field interacts with itself, changes as energy increases. Below energies of about 10 to the 10 GeV, the Higgs self-coupling is positive. This creates the shallow valley where our vacuum sits. But as you increase energy, quantum corrections start to matter. Virtual particles popping in and out of existence affect the field's behavior. Around 10 to the 11 GeV, the Higgs self-coupling turns negative. The valley becomes a hilltop. At these energies, the Higgs field strongly prefers to roll downhill toward a different value, the true vacuum value. This means that if you could somehow give the Higgs field enough energy to reach this scale, it would immediately begin rolling toward the true vacuum. Not through quantum tunneling, but through classical motion over the energy barrier. The most disturbing evidence comes from black hole physics. In 2018, theorists at the Max Planck Institute calculated what happens when a black hole evaporates through Hawking radiation. As a black hole loses mass, its temperature increases. A solar mass black hole has a temperature of just 60 nanokelvin, far too cold to matter, but as it shrinks, it gets hotter. In the final moments before a black hole completely evaporates, its temperature reaches the Planck scale, about 10 to the 32nd Kelvin. At these temperatures, particle energies reach 10 to the 19 GeV, well into the range where the Higgs field becomes unstable. The researchers found that an evaporating black hole could create conditions that destabilize the vacuum locally. The bubble of true vacuum would nucleate at the black hole's location and expand outward at light speed. This means that every black hole in the universe is potentially a time bomb. As soon as one evaporates completely, which takes about 10 to the 67 years for a solar mass black hole, it could trigger the end of everything.